Good day, this is Professor Will, CBMD PhD, today Saturday, June 20th, 2020. It is 11:29 and 1 second a.m. Eastern Standard Time. And this is a continuation of my scientific research on astronomy, so let's get started here. Myself, I had not smoked, had not drank alcohol, had not done any mood-altering substances in my entire life. I got all my brain cells. Doctors are so jealous of me they wish they could be me. Well, this is the first day of summer of 2020, and I'd just like to say it's been a long struggle during the last 30 years of my life. Struggling with psychiatrists who are so jealous of my intelligence that they wish they could be me. So jealous because they don't have the intelligence themselves, so they envy somebody that does. Astronomers detect regular rhythm of radio waves with origins unknown. Signals from 500 million light years away is the first periodic pattern of radio bursts detected. Date June 17, 2020. Source: Massachusetts Institute of Technology. Summary: a team of astronomers has picked up on a curious repeating rhythm of fast radio bursts emanating from an unknown source outside our galaxy, 500 million light years away. Fast radio bursts, or FRBs, are short, intense flashes of radio waves that are thought to be the product of small, distant, extremely dense objects, though exactly what those objects might be is a long-lasting mystery in astrophysics. FRBs typically last a few milliseconds, during which time they can outshine entire galaxies. Since the first FRB was observed in 2007, astronomers have catalogued over 100 fast radio bursts from distant sources, scattered across the universe, outside our own galaxy. For the most part, these detections were one-offs, flashing briefly before disappearing entirely. In a handful of instances, astronomers observed fast radio bursts, multiple times from the same source, though with no discernible pattern. The new FRB source, which the team has catalogued, is the first to produce a periodic cyclical pattern of fast radio bursts. The pattern begins with a noisy 4-day window, during which the source emits a random burst of radio waves, followed by a 12-day period of radio silence. The astronomers observed that this 16-day pattern of fast radio bursts reoccurred consistently over 500 days of observations. This FRB we are reporting now is like clockwork. It is the most definitive pattern we've seen from one of these sources, and it is a big clue that we can use to start hunting down the physics of what's causing these bright flashes, which nobody really understands. In 2017, CHIME was erected at the Dominion Radio Astrophysical Observatory in British Columbia, where it quickly began detecting radio bursts from galaxies across the universe, billions of light years from Earth. CHIME consists of 4 large antennas, each about the size of the shape of a snowboarding halfpipe, and is designed with no moving parts. Rather than swiveling to focus on different parts of the sky, CHIME stares fixedly at the entire sky, using digital signal processing to pinpoint the region of space where incoming radio waves are originating. From September 2018 to February 2020, CHIME picked out 38 fast radio bursts from a single source FRB, which the astronomers traced to a star-churning region on the outskirts of a massive spiral galaxy 500 million light years from Earth. The source is the most active FRB source that CHIME has yet detected, and until recently it was the closest FRB source to Earth. As the researchers plotted each of the 38 bursts over time, a pattern began to emerge. 1 or 2 bursts would occur over 4 days, followed by a 12-day period without any burst, after which the pattern would repeat. This 16-day cycle occurred again and again over the 500 days that they observed the source. These periodic bursts are something that we've never seen before, and it is a new phenomenon in astrophysics. Exactly what phenomenon is behind this new extragalactic rhythm is a big unknown, although the team explores some ideas. One possibility is that the periodic bursts may be coming from a single compact object, such as a neutron star, that is both spinning and wobbling, an astrophysical phenomenon known as precision. Assuming that the radio waves are emanating from a fixed location on the object, if the object is spinning along an axis, and that axis is only pointed toward the direction of Earth every 4 out of 16 days, then we would observe the radio waves as periodic bursts. Another possibility involves a binary system, such as a neutron star, orbiting another neutron star or black hole. If the first neutron star emits radio waves and is on an eccentric orbit, that briefly brings it close to the second object, the ties between the 2 objects could be strong enough to cause the first neutron star to deform and burst briefly before it swings away. This pattern would repeat when the neutron star swings back along its orbit. The researchers considered a third scenario involving a radio-emitting source that circles a central star. If the star emits a wind or cloud of gas, then every time the source passes through the cloud, the gas from the cloud could periodically magnify the source's radio emissions. Maybe the source is always giving off these bursts, but we only see them when it is going through these clouds, because the clouds act as lenses. Perhaps the most exciting possibility is the idea that this new FRB, that even those that are not periodic or even repeating, may originate from magnetars, a type of neutron star that is thought to have an extremely powerful magnetic field. The particulars of magnetars are still a bit of a mystery, but astronomers have observed that they do occasionally release massive amounts of radiation across the electromagnetic spectrum, including energy in the radio band. People have been working on how to make these magnetars emit fast radio bursts. And this periodicity we observed has since been worked into these models to figure out how this all fits together. Very recently, the same group made a new observation that supports the idea that magnetars may in fact be a visible source for fast radio bursts. In late April, CHIME picked up a signal that looked like a fast radio burst coming from a flaring magnetar, some 30,000 light years from Earth. If the signal is confirmed, this would be the first FRB detected within our own galaxy, as well as the most compelling evidence of magnetars as a source of these mysterious cosmic sparks. New test of dark energy and expansion from cosmic structures. Date June 3rd, 2020. Source University of Portsmouth. Summary. A new paper has shown how large structures and distribution of galaxies in the universe provide the most precise test of dark energy and cosmic expansion. The study uses a new method based on a combination of cosmic voids, large expanding bubbles of space containing very few galaxies, and the faint imprint of sound waves in the very universe, known as baryon acoustic oscillations, BAO. It can be seen in the distribution of galaxies. This provides a precise ruler to measure the direct effects of dark energy driving the accelerated expansion of the universe. This new method gives much more precise results than the technique based on the observation of exploding massive stars, or supernova, which has long been the standard method for measuring the direct effects of dark energy. The study makes use of data from over 1 million galaxies and quasars gathered over more than a decade of operations by the Sloan Digital Sky Survey. The results confirm the model of cosmological constant dark energy and spatially flat universe to unprecedented accuracy, and strongly disfavor recent suggestions of positive spatial curvature inferred from measurements of the cosmic microwave background, CMB, by the Planck satellite. This results show the power of galaxy surveys to pin down the amount of dark energy and how it evolved over the last billion years. We are making really precise measurements. Now the data is going to get even better, with new surveys coming online very soon. Researchers say the study also reported a new precise measurement of the Hubble's constant, the value of which has recently been the subject of intense debate among astronomers. We see tentative evidence that the data from relatively nearby voids and BAO favor the high Hubble rate seen from other low redshift methods, but including data from more distant quasar absorption lines brings it in better agreement with the value inferred from Planck's CMD data. First optical measurements of Milky Way Fermi bubbles probe their origin. Date June 3rd, 2020. Source University of Wisconsin-Madison. Summary. Astronomers have for the first time measured the Fermi bubbles in the visual light spectrum. The Fermi bubbles are two enormous outflows of high-energy gas that emanate from the Milky Way, and the finding refines our understanding of the properties of these mysterious blobs. The university measured the emission of light from hydrogen and nitrogen in the Fermi bubbles at the same position as the recent ultraviolet absorption measurements made by the Hubble telescope. Combine those two measurements of emission and absorption to estimate the density, pressure, and temperature of the ionized gas, and that lets us better understand where the gas is coming from. Extending 25,000 light years both above and below the center of the Milky Way, the Fermi bubbles were discovered in 2010 by the Fermi Gamma Ray Telescope. These faint but highly energetic outflows of gas are racing away from the center of the Milky Way at millions of miles per hour. While the origin of the phenomenon has been inferred to date back several million years ago, the events that produced the bubbles remain a mystery. Now, with new measurements of the density and pressure of the ionized gas, researchers can test models of the Fermi bubbles against observation. The other significant thing is that we now have the possibility of measuring the density and pressure and the velocity structure of many locations. We can do an extensive mapping effort across the Fermi bubbles above and below the plane of the galaxy to see if the models that people have developed are holding up. Because unlike the ultraviolet data, we are not limited to just specific lines of sight. Researchers say the work demonstrates the usefulness of the WHAM telescope developed at the UW-Madison to tell us more about the workings of the Milky Way. The central region of our home galaxy has long been difficult to study because of the gas blocking out view, but WHAM has provided new opportunities to gather the kind of information we have for distant galaxies. There are regions of the galaxy we can target with very sensitive instruments like WHAM to get this kind of new information toward the center that previously we are only able to do in the infrared and radio. We can make comparisons to other galaxies by making the same kind of measurements toward the center of the Milky Way. Good day, this is Professor Will, CBMD PhD on infectious disease, molecular microbiology, and astronomical physics. Well, hope you enjoyed listening. Until next time, have a great day.